Hello everyone. In this video, we will quickly review what is an autonomous differential equation, what is an equilibrium solution for autonomous differential equation, and how we can find the type of equilibrium solution. And then we will do some examples. Let me start with autonomous differential equation, a first order differential equation that can be written in this form. The derivative is function of u. So du dt in general can be a function of the independent variable and the dependent variable or unknown. But when there is no explicit dependence of du dt to the independent variable t, then we call it autonomous. So in other words, you have du and du dt, the derivative equals to a function of u only. Okay, there is one thing here that you have to see, that autonomous differential equations DEs are separable. So in other words, we can solve these guys du dt. Well, at least we have a method to find a solution. But what we notice right away is that, okay, so this is how we solve separable differential equations. And what you notice is, oh, I have to integrate an integral like this. And that function can be any kind of function, while in particular it can be polynomials of higher order. And solving such different integrals or integrating such functions are not always easy. So that's why we are trying to find methods in which, without solving the differential equation or integrating function like that, we can discuss how the solutions of that differential equation may look like. Okay? Well, in particular, there is this very specific solutions for autonomous differential equations. These are called equilibrium solutions or equilibrium points. These are solutions for which u prime is equal to 0. In other words, our derivative doesn't change. Since u prime is equal to fu, that means that to find those guys, we have to set right hand side, which is function of u equal to 0, and solve it for u. So these will be, u will be some constant, if you can find those ones, and those are called equilibrium solution, or just simply equilibrium. And well, as I said, when you have equilibrium, these guys are going to be solutions which are constant. So, well, something like you had, say there's one, there's another one, and those are important for us in our study of solutions for autonomous differential equations. There are two types of, or at least the two types that we are interested in, two types of equilibrium solutions. One is called stable, the other one is called unstable. So basically what you do, you try to see what happens to your function. Remember that u prime was equal to fu. So you graph this function. In other words, you set up u prime system of coordinate, and then equilibrium points are the points at which the fu is 0. So the graph of this function will intersect the coordinate or horizontal coordinate. Now, we are interested either in cases like this or cases like that. The cases for which the was the function was positive before you had and then negative after that in a neighborhood, then you had in this case is stable. If before you had the function is negative, then it becomes positive, then it's called u hat is unstable. Well, just to keep in mind one physical case which pictures stable and unstable. Consider a ball which has a ball inside, and an umbrella which has a ball on top. So if I start moving, so we can make sure, so in those cases, both of them, the ball stays at that specific point, at very top or at very bottom of these two cases. But then if you shift the balls a little bit, either to right or to left, what happens in this case? The ball will start oscillating up and down and go back to this one. So that's called stable, because if you change a little bit, it will go back to the original. But in the other case, if you shift ball a little bit to the left or to the right, will continue going away from that point and go to another point. Okay, so that is unstable. So that's just having two things, but mathematical definition, it's an equilibrium point for which the function f goes from positive to negative, it's called stable. Going from negative to positive, it's called unstable. Okay, so let's do these in some examples. Here, first of all, you notice that this is autonomous, and our function, well, in this case, its function of y is y squared minus y minus 6. So the equilibrium points or equilibrium solutions, you find them by setting fy equal to 0. So it means that y squared minus y minus 6 is equal to 0. Well, note that I can decompose this to negative 3, y negative 3, and y plus 2. And then from there you get y is 3 and y is negative 2. So there are two equilibrium solutions, y equal to 3 and y equal to negative 2. Then we want to see what kind of equilibrium points are these ones. So we have to determine what happens to f. What is the sign table of f closer to these points? So negative 2 here, 3 there. And then, okay, evaluate these guys in some values. Here you also notice this will be positive, negative, positive. Okay, so what does this mean? This means that the function goes from positive to negative. This means that function goes from negative to positive. This, by definition, is stable. And y equal to 3, by definition, is unstable equilibrium solution. Well, you could have done this because this is an easy function. You can sketch that, yes. That is just a parabola, and you get negative 2 here, 3 somewhere there. It will be something like that, and you see that goes from positive to negative. That's why it's stable, and this is unstable. But in general, keep in mind that you need to find the sign table for the function. Let's do another example. Here if u is this one, so to find equilibrium solutions we said if u equal to 0, so this means 25u minus u cube is equal to 0. If I factor out u, I get 25 minus u squared, and this is equal to 0. That means that either u is 0 or u 25 minus u squared is 0, from which you can either see 5 is 5, u is 5, or u is negative 5. Now we have to find the sign table for fu. 25u minus u cube. So we have negative 5, 0, 5. You can evaluate this function at middle points, or you use any technique to find the signs here. What I know that it will start from negative here. For example, if you plug in 6 there, you will notice that that's going to be negative. Then positive, plug in 1, you see it's positive. Then you plug in negative 1 or any negative number between negative 5 and negative 5 and 0, you get a negative number, and then again it goes back to positive. So here you see that it goes from positive to negative, so u is equal to negative 5 is stable. Here it goes from negative to positive at that point, so u is 0 is unstable. And here you see that it goes from positive, going from left of 5 to right, it goes from positive to negative, so u equal to 5 is another stable equilibrium. Okay. Again, if you know how to graph this function, that's another way of doing that. But I will again suggest that you do the sign table for the function to determine when it is stable, when it is unstable. Let's do one more. Finding equilibrium. You said if u equal to 0, so that means u cubed minus u squared is equal to 0. That means that if I factor out u squared, I get u minus 1 equal to 0. So this means either u is 0 or u is 1. So here, then I have 0 and 1. Oops, sorry. Okay. And then this is u cubed minus u squared. Try to find some sample points, but you right away notice that bigger than that, this will be 0. Less than 1 will be negative, and then less than 0 will stay negative. For example, try it for negative 1. You notice that it's a negative number. Okay. So what happens here is that here the function was before 0 was negative and stays positive after, so it will be something like this. For this one goes from negative to positive. So right away this one tells me that u equal to 1 is stable. Oh, sorry, unstable. Wow. Unstable equilibrium. But for this one, it neither goes from positive to negative nor goes from negative to positive. So it's nor stable, neither unstable nor stable. So this doesn't fit in any of two types that we have studied. Okay, so these were some examples and very quick review of the content, specifically fixing the type of equilibrium solutions for an autonomous differential equation.